Hello everyone, I'm Rishabh. Today we have a topic of electromagnetic induction, that is Faraday's law. So let us first write the topic: electromagnetic induction. Induction, and we have a topic of electromagnetic induction, that is Faraday's law. Faraday's law of electromagnetic induction. So before we talk about Faraday's law, let us talk about magnetic flux first. So it is because to understand the Faraday's law of electromagnetic induction, we have to know the basics of the magnetic flux. So magnetic flux. So the general representation of the flux is by phi, and it is a magnetic flux. So we can say phi b. So the basic idea of magnetic flux is the number of field lines passing perpendicular through a surface. It means if we consider a surface, let's say this is the surface, and the magnetic field lines are perpendicular through the surface. So how many magnetic field lines are passing through the surface? 1, 2, 3. So we can say the magnetic flux is equal to 3. And if we increase the strength of the magnetic field, so the density of the magnetic field lines will also increase. It means that the magnetic field lines become closer to each other. So to understand this, let us make another diagram. So for the same surface area, this is just a basic rough diagram, and the magnetic field lines are perpendicular and closer to each other because the strength of the magnetic field increased. So if the strength of the magnetic field increased, the magnetic field lines get closer to each other. It means the number of field lines passing through the same surface area will be with 1, 2, 3, 4, and 1, 2, 3, 4, and 5. So the magnetic flux will be 5. So it means that the magnetic flux is directly proportional to the magnetic field, and also uh, in the second condition, if we increase the area of the surface for the same strength of magnetic field, it means if the magnetic field is constant, and if we increase the surface area, then let's say the surface area is increased, and for this same magnetic field strength, here the magnetic flux will be 1, 2, 3, 4, 5, 6. So here the magnetic flux is 6. So it means that the magnetic flux also depends upon the surface area. So magnetic flux also depends upon the surface area. So from this two uh, from these two results, we can write that the magnetic flux is equal to magnetic field times the surface area, but the actual formula is phi b that is magnetic flux is equal to B magnetic field times area, surface area times cos theta. Here the theta is the angle between the area vector and the magnetic field vector. So here the area vector is the perpendicular or normal to the surface. Theta is the angle between area vector and magnetic field vector. Field vector. So to understand this, let us consider again a surface where the area vector is perpendicular to the surface, and let's say the magnetic field is passing through the surface like this. So the angle between magnetic area vector and the magnetic field vector is theta, and as we can see, the magnetic field is not perpendicular to the surface, so we are going to consider the component of the magnetic field, that is B cos theta, and here B sin theta. So as we can see, the B sin theta is not passing through the surface, only the B cos theta is passing through the surface. So the magnetic flux will be B times area times or area of the surface times B cos theta, and also in a vector form it can be written as the dot product of area vector, magnetic field vector and the area vector. So as we know that this dot product always gives a scalar quantity, so the magnetic flux will also a scalar quantity. Magnetic flux is a scalar quantity. And the unit of magnetic flux will be B A cos theta. So magnetic field has the unit Tesla and area has the unit meter square. So the unit of magnetic flux will be Tesla meter square, and we also say it Weber. We are going to talk about Faraday's experimental observations. So Faraday's experimental observations. So the first observation is that if a coil, if a conducting coil is placed, if a conducting coil is placed in a magnetic field, we are considering the magnetic field. If a conducting coil is placed in a magnetic field, then if the magnetic field is changing with time, here the magnetic field is changing with time, then there will be a induced EMF in a coil. then there will be a induced EMF in a coil, in the coil. And the second observation was, if there is a constant magnetic field, if there is a constant magnetic field is a constant, and the area of the coil is changing, area of coil changing, then there also be a induced EMF in the coil, and there will be a induced EMF in the coil. In the third observation, if a coil is placed in a magnetic field, let's say the magnetic field, and a coil is placed, and if the coil is rotating, then there will be a current induced. If the coil is rotating, then the EMF will induce in the coil. Then the EMF will induce. So in the in rotation of the coil, the area vector, actually there is a change in angle between the area vector of the coil and the magnetic field vector. So here in rotation of coil, there is change in angle between area vector and the magnetic field vector and magnetic field vector. So we can say that the induced EMF in the coil is the magnetic flux. It means the induced EMF or EMF induced in a coil, induced EMF directly depends upon magnetic field, area of the conductor, and the angle between the area vector and the magnetic field vector, which means the induced EMF depends upon the change in magnetic field, change in area, and change in angle between area vector and magnetic field vector. So it means there is a change in flux. We can directly say that there is a changing in flux. It means that if there is change in flux, that is, flux is equal to magnetic flux is equal to magnetic field times area times cos theta. So if there is a change in magnetic flux, then the current will the EMF will induce. The EMF will induce in the conductor. So now let us talk about the Faraday's law. Faraday's first law. And the definition of Faraday's first law is whenever there is a change in a magnetic flux linked with a conductor, an EMF is induced in the conductor. Whenever there is a change in magnetic flux linked with a conductor, and EMF is induced. EMF is induced in the conductor. The conductor. And if a conductor is a coil, closed coil, then there will be a induced current flows through it. There will be a induced current flows through it. And to understand this, there is perfect example. If here is the condition of that example, where a bar magnet is passing has a moment through the coil, and a coil is connected to a galvanometer. We are not considering direction now because um let's it will be the part of the Lenz's law. So if the movement of a magnet is through the coil, you can say that if a magnet is moving through a coil, then there will be a induced current in the coil, which can be shown by the galvanometer or a deflection of the galvanometer. And if in the another condition, if a magnet is moving, if a magnet is stationary and coil is moving, then there also be a current induced in the coil. So we can say that whenever there is a relative motion between the coil and the magnet, then there will be a EMF induced in the coil. So we can write that whenever there is a relative motion between coil and magnet, then there is a EMF induced. And to understand the relative motion, if we consider a situation in which if a magnet is moving with 7 meter per second, and if a coil is moving with 7 meter per second, and the magnet is also moving at 7 meter per second, then there will be no relative motion in between them. so there will be no induced EMF in the coil. And if a magnet is moving, let's say 5 meter per second, and coil is moving at 7 meter per second, then there will be a increase or decrease in magnetic force of the magnet with respect to the coil. So we can say that there will be a induced EMF in the coil. So the motion should be relative to the coil and also the magnet. Now let us talk about the second law, second Faraday's second law. Faraday's second law. So in Faraday's second law, it is a it has a definition that the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux. So if we consider that magnetic induced EMF or magnitude of induced EMF is E, it will be directly proportional to the change in magnetic flux. So change in magnetic flux, rate of change in magnetic flux. So rate of change in magnetic flux means change in magnetic flux upon change in time. So this is a average induced EMF. And if we talk about instantaneous induced EMF, then it will be directly proportional to instantaneous, that is d phi upon dt. And if we remove the proportionality, then there will be a proportionality constant k d phi upon dt, and where k has the value 1. So the instantaneous induced EMF will be d phi upon dt. And actually there is a negative sign which represents that the induced EMF has the different direction to the magnetic field, or the opposite direction to the magnetic field, which will be introduced in the Lenz's law. But we are just writing this here to understand this equation. So if we take the magnitude, if we are just talking about magnitude, then there will be a mod sign here. So it will be mod d phi upon dt. So we are just taking the magnitude of the rate of change of magnetic flux. And if there is a resistance in a coil, let's say if the resistance of coil is if the resistance of coil is R ohm, then the current will be delta V, that is change in potential difference, upon R. So it will be induced EMF upon R. So the instantaneous current The EMF is just a potential difference in the coil. So we are writing that the induce the potential difference as a induced EMF. So the instantaneous current will be equal to induced EMF is d phi upon dt times 1 upon r. So this is the first and second law of Faraday's on electromagnetic induction. So that's all for now, and in the next video we will be doing some numericals on the Faraday law of electromagnetic induction. So I hope you understood. Thank you.